Howdy, everyone. Happy sunny Wednesday. I hope you're all doing well and more or less getting back to normal as much as we all can. Um, just as a reminder, a week from today, we have our first examination. Our next class, Friday, we will have a review for the first exam. Uh, I have sent you an email with the review, and we'll be going over that. I have also sent you a bunch of practice problems, which you should be doing. If you do all of those, you should be able to do almost any kind of problem that you might anticipate seeing on the examination. This cartoon hopefully reminds you of what we talked about last time, namely how the Doppler effect uh, has been very helpful for us to understand the nature of the universe, and seeing how the Doppler effect affects the spectra of the hydrogen atom. We're able to tell that we have an expanding universe, and then ultimately tell that the universe is 13.79 billion years old. The cartoon also reminds me of a bad joke. So it's a riddle. If you know the answer, send me the chat. But the riddle is, what did Obi-Wan Kenobi of Star Wars fame say to the Texas cowboy? So I'll wait 10 seconds to see if anybody has an answer. Okay, 1, 2 chats. Let's see what we come up with. I'm getting a couple of hello there. Well, what Obi Kenobi said, may the horse be with you, of course. He could have said howdy too, I guess. That would have been more or less appropriate. Okay, so I've been having some problems with my home computer and PDFs, so I apologize if any of that pops up, but I think we should be able to do okay. We have to rush a little bit, as you saw what we did last time, but let me remind you what we're doing now. So in the background, we have the variation method, and the variation method says we try a trial function for a wave function and see how it does. The lower the number we get, the closer it'll be to the real value, because the trial function, if it isn't the exact wave function, will always give us an energy that's higher than the actual energy. So as an example, we started off with H2 plus. Our trial function looked like this. We're combining two of the 1s orbitals on two different nuclei. And we're going to see if we can then smush them together to come up with what the molecular orbital would look like and what it would be. So we went through the variation method. This is the formula for it. Here we're sticking in psi as our trial function. We get a bunch of integrals. We get a formula for the energy. We examine what some of these individual integrals are. And then we get another form for the energy. And notice that what this has in here are terms like J and K, which are integrals dependent on the distance between the two nuclei. And then we also have this repulsive term. So to find the best energy that we can, we want to minimize this, because we know the minimum energy we can calculate will be closest to the real value. So to do it, our two variables are the coefficients C sub A and C sub B. These represent how many times we take each of these orbitals. And to minimize the energy with respect to these, then we set the derivatives equal to 0. That gives us two simultaneous equations. We call this a secular determinant, and then we solve this. Later, when we look at larger systems, we're going to start off with a lot more than just two orbitals, and oftentimes we'll have a secular equation or secular determinant that may have more than 100 rows or 100 columns, or even thousands of them. But that will give us very good answers. All right, well, the bottom line is we find that one energy level, which we're going to call the bonding energy level, is given by this formula here. It's can be equated to what the energy of the electron would be on the free hydrogen atom. And it's got the repulsive term between the two protons. And then J and K are integrals, both of them negative, which depend on the internuclear distance. And then we graph this, and this is what it looks like. Everything in nature always wants to go to its lowest possible energy. So the molecule is smart. It finds the lowest possible energy for this bonding orbital. It picks the correct distance for the bond distance between these two protons. And it's going to be something like half an angstrom. But whenever we start from two atomic orbitals, we also generate two molecular orbitals. So this was the one, the bonding one, but we also generate an antibonding orbital. So this is how the antibonding orbital energy changes. So where we finished last time, I pointed out that the main source of energy, the thing that brings this total energy down for the molecular orbital, is this so-called resonance integral, which we call K. And this allows the electron to be on both nuclei, because here we have the electron on nucleus A, here we have it on B, and then one or the other of the protons attracts this. This could either be attraction by A or attraction by B that we have on the right-hand side. Okay, so this is what we came up with, and then this was my picture trying to depict what this looks like. We're taking a 1s orbital on the left, a 1s orbital on the right. We're smushing them together. The black dots here in this thing that looks like a Zorro mask represent where the two nuclei would be. But we get enough negative charge between the two positive nuclei that we get a bond coming out of the system. As we're going to see, when we go to the hydrogen molecule, when we have two electrons, we get even more negative charge between these two nuclei, but basically we're going to have the same orbital for H2. The other orbital, because the wave function on the left is positive and the wave function on the right is negative, it's going to have a node. That means the wave function goes to 0. And the probability right in between here will not allow any electron density to occur. And it's not always 0, but even when it's very close to 0, you have very little negative charge. And so that these two protons are going to repel each other. And this would be a repulsive or so-called antibonding orbital. I think we also talked about the hydrogen atom last time. You should be able to write the potential energy terms. The negative ones are the attractive terms, where protons attract the electrons. And the plus terms are the repulsive terms. Between either the two electrons or between the two protons. Negative numbers are good. We always want to go to the lowest possible energy that we can. All right, so we tried some trial functions to see how we would do for the hydrogen molecule. We didn't like this one because it was too restrictive. It had electron 1 on A, electron 2 on B. So we improved it a little bit and said, let's allow both possibilities. This has 1 on A, 2 on B, or 2 on A and 1 on B. So that was pretty good. We get a lot better answer from our trial function using the variation term. But to make it even better, we want to add the possibility of an ionic term. This represents both electrons on A. This represents both electron 1 and 2 on B. And so this would be the function that we would have for our trial function. But to improve it even one notch further, we can note that the ionic part, just intuitively, we know is going to be less important than the covalent part. And so we could vary these constants, C for covalent bonding, C for ionic. We expect the covalent bonding to come out stronger, and then this would give us the best bonding that we can have. So this is pretty much the background to everything that we're going to be doing. So to continue, then we're going to call this the molecular orbital approach. Again, this is the linear combination of atomic orbitals, or LCAO. For H2 plus, we found that the lowest bonding orbital would be adding the two 1s orbitals together. The antibonding orbital is when we took them with different signs. Now, many of you may say, what the heck does that mean, that one is a negative wave function, one is positive? A lot of this is a mathematical game. We're talking about waves. Waves can have nodes, and this is what makes the answers come out the way they're supposed to be quantum mechanically. So it's pretty hard to have an intuitive sense other than maybe looking at this kind of picture that we have here. If we go to plus to minus, you can see the probability has to go to 0 at some point in between. Okay, so a model that we can write is, let's simplify the nomenclature a little bit, and then I'm going to change it again. Instead of writing psi sub g, let's just say the first orbital is sigma sub g. And you're going to see why I call it sigma, because it's going to be a sigma type single bond kind of thing. So we'll say sigma g is just this orbital here. And then for the second one, we'll call it sigma u, but we'll also put a star on it, and it'll be antibonding. And I apologize, this is the same looking star that we use for complex conjugates. So it doesn't mean at all the same thing. Here it just simply means we're going to refer to antibonding orbitals by psi star. Okay, so when we get to molecular orbitals, it's going to work out, again, according to the Pauli principle, that we can only put 2 electrons into each orbital. Ultimately, it goes back to whether the overall wave functions are symmetric or anti-symmetric with respect to exchange. But if we want to write the overall molecular orbital scheme for the hydrogen molecule now, we'll put electron 1 into the sigma g orbital, and we'll put electron 2 into the sigma g orbital. Notice that the sigma g orbital is made up from contributions from both atomic orbitals, 1sa and 1sb, one from each atom. So we're not violating the problem that we had before by being too restrictive by trying to put both of the electrons on the same atom. These are still going to be shared as such. Mathematically, it means it looks like this. And if you multiply this out, you're going to see that it's exactly what we have at the top of the page right here. So this is the representation that we're basically writing for a molecular orbital scheme. Okay, so we're going to start an Aufbau scheme for homonuclear diatomic molecules. Homonuclear means the 2 atoms are the same. Here they're both hydrogen atoms. Aufbau is the German word for building up. When you learned the scheme for atoms, 1s2, 2s2, 2p6, 3s2, and so on, that was also called an Aufbau scheme. You may or may not have called that in freshman chemistry. All right, so at this point, I want to now go into the nomenclature that we're going to use, and also tell you there are a number of other nomenclatures that can be used, including one in the book, which I don't recommend. We've just said sigma g is basically adding the 2 1s orbitals together. Sigma u is having a minus sign for the second orbital. Okay, so what we can see is we've created 2 orbitals, and we're able to put 4 electrons into these first 2 orbitals. You might say, well, we don't want to put electrons into antibonding orbitals, but Mother Nature decides sometimes we do. So let's see how this is all going to work. But first, let me tell you the nomenclature that I want to use. I'm going to use that sigma g, which ultimately looks like 1sa plus 1sb. We'll call that a 1s sigma orbital. So the 1s sigma, the 1s tells us which atomic orbital it comes from, and then sigma tells us which type it is. We're going to wind up with sigma orbitals or pi orbitals. If we went further into molecular orbital theory, we'd also have delta orbitals, which could use d orbitals, for example. Okay, so sigma G, we're going to call 1s sigma. The sigma U, I should have probably labeled this sigma U star, we're going to call it 1s sigma star. So I find that this nomenclature is very straightforward. I personally actually like to write the 1s as a subscript, so we could write this as sigma 1s and sigma 1s star. But when we write exams and stuff, it's kind of a pain to go into subscripts and put numbers on it and so on. So let's stick to the nomenclature I have up above. If you go to some other books, they like to keep the G's and U's. They might call this a 1s sigma G or a 1s sigma U star. So any of these choices are okay. Now the book uses a nomenclature that in a way is more universal, but it's much less descriptive. So what the book does, it just consecutively numbers the orbitals. So the first orbital made up from the 1s's, it just calls it the 1s sigma. It doesn't remind you that it comes from the 1s orbital. Then the next orbital, it calls it 2 sigma star. It does have it as a star because it's anti-bonding, but the 2 just means it's the second orbital that one can have. Some books will call this 1 sigma G and then 2 sigma U, but you lost track of where it comes from. So this is why I no longer like it. The advantage of the book method is that when you no longer have homonuclear diatomics and your 2 atoms are very different, then your orbitals don't exactly look like 1s sigma and 1s sigma star. But if the 2 nuclei that you're bonding are still pretty close, like you would have in NO, nitric oxide, or CN, cyanogen, then the method I'm proposing still will work quite well, and we'll see how it goes. Later on, you're going to be assigned problems from your book to write schemes. I strongly recommend using the scheme that I'm going to be using. Don't try to understand the book one, because I think you'll just confuse yourself by doing that. Okay, well, let's keep this in mind then. So how would we use the Aufbau scheme for homonuclear diatomic molecules? H2 plus, we have 1 electron, so we put it in the 1s sigma orbital. Again, this is the one that looks like this. So this is made up of the 2 1s orbitals smushed together, and that's where we put our electron. Down here, note I'm saying a bond order is defined as 1/2 the number of bonding electrons minus the number of anti-bonding electrons. So this is essentially confirming what you learned in freshman chemistry. It takes 2 electrons to form a bond. So we're going to say H2 plus creates half a bond. We can then go to H2. We'll put both of those electrons in the 1s sigma orbital. So we'll have a bond order of 1. 1/2 of 2 is 1. Notice this would also work for helium-2 plus 2. We'd have 2 plus charged nuclei on the helium. And if we strip off 2 of the electrons, make it a plus 2, it still would be a 2 electron system. And this molecule has been made on Earth. It exists quite commonly in space also. But we can see that we'd expect to be a fairly stable molecule with a bond order of 1. Reason we don't see a lot of this on Earth is because it can easily go to more stable forms, just like plain old helium atoms themselves. Well, the H2 minus molecule also exists. This has been made on Earth, as has the helium-2 plus. Both of these systems have 3 electrons, and so they would have the scheme 1s sigma squared, 1s sigma star 1. Now notice we're utilizing an antibonding orbital. This is not anything you ever learned in freshman chemistry, but as we'll see as we go along talking about bonding, and later when we talk about electronic spectroscopy, these orbitals do exist. We can have transitions of electrons from bonding orbitals to antibonding orbitals. And that's where a lot of the color of the universe comes from. We have absorptions taking us from a ground state to an excited state where an electron goes into an antibonding orbital. Okay, well, the bond order of this is 1/2 of 2 minus 1, or 1/2. And so this will exist, but it won't be very strong. Helium-2, we cannot make. This would have the configuration 1s sigma star, 1s sigma star squared. The bond order would come out to be 0. So this is non-existent. Later in the course, when I tell you about excimer lasers, I will be telling you that we can actually make excited states of helium-2. And we do that by taking one of the antibonding electrons and exciting it to a higher bonding electron. That probably seems strange to you right now, but these helium excimers can actually exist. Okay, so this is what we have in terms of an energy diagram. And make sure that you understand the concepts shown here. So this is kind of similar to what I've shown you before. Usually I've just shown you an energy diagram with one set of energy levels. Here I'm showing you 3 sets of energy levels. On the left we have atom A, it's a hydrogen nucleus, in the case of H2. On the right I have atom B with its 1s orbital. So the orbitals we're creating are, one is a bonding orbital, and it's lower in energy than the 1s orbital in the hydrogen atom. And then we create an antibonding orbital that's higher in energy. So let me jump back to this curve that I have here. So notice this is the energy of the hydrogen atom. So if we're going to get any stability in a molecule, the electron from a hydrogen atom has to go to a lower energy in the molecule. And we can see that that would be this drop in H2 plus by having it lower. The antibonding orbital at this R that the molecule chooses will be at a higher energy. And this is typically about the same amount of higher energy as this is lower. So that's what we're representing by this diagram here. We start from 2 atomic orbitals. We create 2 molecular orbitals. One goes lower in energy, and that's where we prefer to put our electrons, but one goes higher in energy. So just as an example of how it would work, first let me tell you, if we do H2 plus, we put 1 electron here at 1s sigma. If we form the hydrogen molecule, H2 up here, we put both electrons in a 1s sigma. On the right, I'm showing you where the electrons would go for H2 minus. So 2 electrons get lower than the hydrogen atom energies. 1 electron goes higher. We still gain some net stabilization by having these electrons go into these molecular orbitals, and we will still have a bond. Obviously, if H2 minus would kick off its electron, we would have a stronger bond, and H2 is stronger bonding than H2 minus. Later on, after I talk about some other diatomic molecules, I'll show you a table with relative energies that we have for different bond orders that we have for these molecular systems. So again, make sure that this concept is clear for you. If it's not, read the book some, but try to think about how it works there, that we get 1 orbital lower in energy, and then we get an antibonding orbital of higher energy. So in the middle here, these are the molecular orbitals that we're generating for the molecules that we have. Okay, so here's our pretty picture, or not so pretty, however you choose. Start on 1s orbital on A, 1s orbital on B, we smush them together. The plus signs indicate that we have plus wave functions. They do not have anything to do with charge. So the electron is always minus, we're looking at the energy of the electron. As you remember from the Bohr-Oppenheimer approximation, we're not caring so much about what the nuclear motions are and what the nuclear energies are. So the plus sign indicates the sign of the wave function. Now, if we take a plus 1SA and a minus 1SB, then this is what we get. And notice we have to have a node in the center because the plus wave function has to go to 0 in order for it to become negative on the right-hand side. So we get repulsion between these two protons that we have here. In brackets here, I parenthetically said, as far as the mathematics go, we could just say we add a 1SA orbital with a plus sign to a 1SB orbital with a minus sign. So it doesn't have to be a minus here. Orbitals themselves are equivalent, whether they have plus wave functions or minus. So either way is mathematically equivalent. If that's confusing, just ignore what's in brackets, but it's a statement of quantum mechanics. All right, well, we can't get very far with just 2 orbitals. We can only look at putting in 4 electrons. So let's work our way up and see what happens with diatomic molecules and learn about the nature of bonding in general. Well, the 2s orbitals are going to combine almost exactly the same way. The 2s orbital looks pretty much like that, except you'll remember close to the nucleus there is a node, and so they're still spherical, but there's a slight difference in where the orbitals are. They're also going to be larger. The electrons are going to be further out. But we can make the same kind of combination. 2SA plus 2SB will give us a 2s sigma orbital, and 2SA minus 2SB will give us 2s sigma star. Now, notice why I like this nomenclature. Now we know exactly where these orbitals come from. Your book would call this orbital 3 sigma, and this one would be called 4 sigma star. And you've lost total track of where these orbitals come from. Okay, so we have 2 more orbitals, so we can add 4 more electrons into our scheme if we want. Helium-2 minus would have 5 electrons, would have this scheme. So you remember we had the 1s sigma squared, 1s sigma star squared earlier for the 4 electrons. Next one goes into 2s sigma 1. Next comes lithium-2 with 6 electrons, 1s sigma squared, 1s sigma star squared, 2s sigma squared. Notice the bond orders. This would be bond order of half. This would be a bond order of 1. So here we have 4 bonding electrons, 2 anti-bonding. 4 minus 2 is 2. Take half of that. You get a bond order of 1. Now, many of you probably not only saw chunks of sodium thrown in the water in high school and get hydrogen gas off, which probably got ignited. You might have also seen soft lithium being cut up and tossed in the water and had the same reaction. It turns out lithium vapor is very easy to form. Solid lithium just has a lot of atoms joined to each other with intermolecular interaction. But if you gently heat lithium solid, you can form lithium-2 diatomic molecules like this. And it's been very thoroughly studied. People understand the bonding. And again, as I'll show you later in a table, that its bond order should be about 1. Okay, so that's how orbitals are almost trivial to look at. We just kind of bump circles together and then make a blob, an ellipsoid, something like that, and that's going to be our bonding orbital. And then the anti-bonding ones have to have separations in between. Okay, so well, let's stop here with the 2s orbitals. Okay, let's now look at p orbitals, and I'm sure you learned about this in organic chemistry. When you form bonds in organic molecules, you probably talked about hybrids, but for our purposes, we're not going to be generating hybrids just now. We don't have to. So we're going to try to make straight bonding interactions between p orbitals. Some of the p orbitals will point to each other, like in my top model here, and then others are going to be perpendicular, like you learned in organic chemistry, to form pi bonds in molecules like ethylene and acetylene and benzene and so on. So let's form the sigma bond first. And so the bonding axis by convention in diatomic molecules is called the z-axis. So we'll call this 2pz on A, and we'll call this 2pz on B, and we'll point the wave functions with the plus signs towards each other, and that will form the bonding orbital. Keep in mind, we don't want to get any nodes, so we want plus going to plus. And so this will be the shape of the orbital that we have. We have a plus here indicating the plus sign of the wave function, but it's all going to be negative charge. And so the two black dots representing the two nuclei, they're positive, will be attracted to the negative charge in between in this bonding 2p sigma orbital. The little negative parts of the p, atomic p orbitals wind up outside the bond here, and there still be electron density out there, but the important part is we get negative charge between the two nuclei. Well, just as we had for the s orbitals, anytime we make a combination of two orbitals, two atomic orbitals, we have to generate two molecular orbitals. So here comes our second one, and it's going to be anti-bonding. This combination comes from a mismatch of plus wave function going to minus wave function. If we try to smush these together, again, we're going to have to create a node in between, and we're going to wipe out and cancel a lot of the probability between the plus sign here and the minus sign here. And so this is more or less what the anti-bonding orbital would look like. A node in the center, and then two exposed nuclei that are plus charges repelling each other. So this would be an anti-bonding repulsive orbital when you put electrons in it. But sometimes you'll see we have to put electrons into it if there are too many just for a system. Okay, so we get these two orbitals from the two p's. But as you learned again in organic chemistry, you can have pi bonds. And so pi bonds in these diatomic molecules can be two lined up like this, or they can be lined up sideways. So this is sort of like what you learned for acetylene, that you have a triple bond. A pair of the bonds come from pi interactions. One comes from a sigma interaction. So we can line up the p orbitals perpendicular to the bonding axis like this, and this would be the 2p pi y that we call it. We have the y-axis going up and down. And we would also then have to generate the anti-bonding 2p pi star orbital. And again, notice in the anti-bonding, this has a plus sign, this has a minus sign, so that has to be a big area of very low and zero probability. And so these blobs just kind of wind up pointing away from each other. We have a lot of repulsion between the nuclei, so this is anti-bonding. And of course, we can point these orbitals in the opposite or in the perpendicular direction. So these are meant to be coming out of the screen. We've called this the x direction. And if the wave functions match, we can form the 2p pi x orbital, and it'll have equivalent energy as the 2p y. So think back to what you learned in acetylene. These would have been what the pi orbitals looked like in your acetylene system. And here then is our anti-bonding counterpart. I've tried to put this plane coming out of the screen as such, but again, because minus sign doesn't match up nicely to plus, this becomes an anti-bonding orbital. Now, we've talked about degeneracy before. You remember we talked about the three-dimensional particle in a box, and we could see that we had a lot of energy levels that had exactly the same energy. These 2p pi orbitals and 2p pi, the 2p pi x and the 2p pi y are equivalent in energy, and so we say that they are degenerate. So this can get a little bit confusing when we get to using the Aufbau scheme, because sometimes we get lazy and we forget to write x and y on 2p pi. And we might just say there are 3 or 4 electrons in a 2p pi orbital. But it really would mean we have 3 or 4 electrons in the 2 orbitals, this orbital and that orbital, but they are exactly the same energy. Okay, so this is as far as we're really going to go in this course. I think you can readily see that we could next go to 3s orbitals, and we could make 3s sigma and 3s sigma star orbitals. Then we could make 3p sigma orbitals, 3p pi orbitals, and then we could also get to 3d orbitals. But that gets into more advanced looking at molecular orbital theory. What I'm going to tell you next, I think, will be clearer when I show you some diagrams soon. But for now, let me just state what the rule is. The order of these orbitals is pretty much intuitive, except for one pair of orbitals. And this is the question of whether the 2p pi or the 2p sigma orbital is lower in energy. And this is because of the fact that the orbital 2p sigma is very sensitive to what the nuclear charge is. And so if the nuclear charge is relatively small, meaning that in your homonuclear diatomic molecule, each nucleus has no more than 7 protons, the 2p sigma is higher in energy than the 2p pi. When you get to more electrons, like you would for the O2 molecule or F2 molecule, the 2p sigma drops below the 2p pi. So as I said, this is pretty much the intuitive order that you would have. I'm introducing you here also to the shorthand nomenclature that sometimes we get tired of writing 1s sigma squared, 1s sigma star 2. First 4 electrons go in there, and that's just written as H2 bracket. You'll see that your book does that also quite often to minimize the overall description of the orbitals. But just to see how this works, and we're about to we're actually not about to run out of time. We have another 12 minutes. Let me show you the diagram that we have for the for the oxygen molecule. So on the left, we have oxygen atom A. On the right, we have oxygen atom B. And here we have the molecular orbitals for O2. The book that I took it out of ignored the first 2 orbitals. And that's probably the way that your book has it. So to confuse life even more, they started orbital labeling at the 2s sigma level. If they'd started down here, that would be called a 3 sigma orbital. So this is the scheme that I don't like and your book uses, and I hope you agree with me that this is a lot harder to understand. According to our scheme, our orbitals, when you have more than 14 electrons, are 1s sigma, 1s sigma star, 2s sigma, 2s sigma star, 2p sigma, 2p pi, 2p pi star, 2p sigma star. And notice the degeneracy that we get from the 2p orbitals. First, we get the sigma orbital down here, but then we have a pair of orbitals, and that's what this double line is supposed to represent. They're exactly the same energy, but we can put in 4 electrons into the 2 orbitals. and you can see how they're paired. So we'll look at oxygen again later, but notice oxygen, each atom has 8 electrons, so we have 16 electrons to put into the system. So we have 2, 4, 6, 8, 10, 12, 14, and so we have 2 left electrons to get up to 16, so this would be electron 15 and 16. So I'd like showing the oxygen molecule right off the bat because this shows clearly the power of molecular orbital theory over Lewis dot structures and other schemes that you might have run into for bonding. So we count up all our electrons, and then we have 2 electrons to put into the 2p pi star orbitals. They are exactly of the same energy, and the same Hund's rule that you learned in freshman chemistry about putting electrons into different orbitals tells you we will now put 1 electron into one of the 2p pi star orbitals, and we'll put the other electron into the other 2p pi star orbital. Hunt also tells us the electron spins will be in the same direction. Think back to what you learned about the nitrogen atom in freshman chemistry. You had 1s2, 2s2, 2p3. The 2p3 meant you put 1 electron into each of the 2p orbitals, and they all had the same spin in the same direction. Well, what's the significance of that? Unpaired electrons cause paramagnetism. It's a fairly strong kind of magnetism. It's not as strong as ferromagnetism when you're picking up nails with a magnet, for example, but it's quite strong in molecules. It's quite easily detected, and it tells us a lot about the characteristics of molecules. So the oxygen molecule is paramagnetic. Hopefully all of you have been following NASA's landing of rover onto Mars this week, which should turn out to be quite exciting. In the early days of NASA, when I was about your age, NASA was sending up rockets. About half of them were blowing up. And they fairly soon discovered that one of the problems was they were using liquid oxygen as a fuel. They had electronics in their system. The paramagnetism of the oxygen was fouling up the electronics. And so things weren't going quite as they expected when they pumped in the liquid oxygen into the rockets. They soon learned from that, and the rockets quit exploding, but it was pretty challenging in the early days as we had the space race with the Russians, which ultimately the US beat the Russians to the moon. If I'm correct, I'm not even sure if the Russians had ever even sent anyone to the moon at this point. The Chinese have, I know, but I haven't kept track of the Russians. Anyway, hopefully you see what the importance of this scheme can be by looking at this. Okay, well, this fuzzy gray diagram is very hard to decipher. I think it may be out of your book or a similar book. Again, it shows a different nomenclature on the left, starting labeling at 1s sigma g here. And then I have put my labels. Hopefully they're still in your lecture notes. But if they're not, the next page of the notes will correct all this. Okay, so here's a scheme for a bunch of homonuclear diatomics, starting with lithium, ending with fluorine. In each of these cases, I've shown a different nomenclature. The nomenclature on the left starts by ignoring the first 4 electrons. This is what's called helium-2 electron structure for the first 4 electrons, even though helium-2 doesn't exist. I like to include them just for completeness. These are 1s sigma, 1s sigma star. So this is the scheme. Now notice this is the 2p sigma orbital. It starts way higher in energy than 2p pi when we have lithium. Lithium has only a +3 charge on each nucleus. Boron has +4, sorry, beryllium +4, boron +5, carbon plus 6, and so on. So you can see this orbital rapidly drops. Finally, at oxygen, which I just showed you, the 2p sigma is lower than the 2p pi, and it's even further lower when we get to fluorine. Most likely on your second exam, I will ask you to write the electron scheme for some diatomic molecule. And so you need to be aware of how the scheme changes a matter of nuclear charge. In this diagram, I've also stuck in a couple of heteronuclear, actually even only one. I've stuck in one heteronuclear molecule, Cn. And that's just to show you that the orbitals would still be very similar that you have. Because carbon and nitrogen orbitals are very similar in size and energy. And so when you combine them, you can still label them according to the scheme that we have on the right-hand side. Later on, I'll tell you about diatomic molecules like hydrogen fluoride or other systems, like maybe BO. Those don't work quite as well. But when the atoms are close together in terms of their Z number, then the scheme pretty well works. On the bottom here, I put a summary. So for each of these, you should be able to calculate the bond order. This comes simply from counting the total number of bonding electrons minus antibonding. And from the diagram, you can also count the number of unpaired electrons, which will tell you if the system is paramagnetic or not. So if we take the Cn system, carbon has 6 electrons, nitrogen has 7 electrons, we have 13 electrons. 4 down here, 6, 8, 10, 12. 13th electron goes there. You can see we have a total of 5 net bonding electrons over antibonding, so this would be a bond order of 2.5. If you go in pairs, these two cancel each other out in terms of bonding and antibonding. 2s sigma and 2s sigma star cancel each other out. So all 5 of these electrons are net bonding electrons, or bond order of 2.5. Many of you have learned before, one of the most stable molecules ever is N2. It's got a triple bond, and you can see why. If you go to oxygen, oxygen only has a bond order of 2. Now, in freshman chemistry, you would have calculated or written a dot structure that showed a bond order of 2, but you would have also shown that each oxygen atom had 4 unpaired electrons, and it would not have told you anything about the fact that 2 of these are in antibonding electrons. You would not have known it's paramagnetic, and you would not have known that you could have had transitions, say, from the 2p sigma orbital to the 2p pi star orbital, and that would absorb some ultraviolet light, for example. So there's a lot more to this scheme than you might think, but it's the basis of really having a much better understanding of how bonding takes place. Okay, so make sure you study when the time comes this diagram thoroughly. And I'm seeing lots of chat questions. I had that covered up with things. Let's see what we have. Okay, how do we get 2.5 for boron oxide, or Cn? You count up the total number of bonding electrons, you subtract from that the number of antibonding electrons, and you divide by 2. Someone asked me about a white arrow. Where did we have a white arrow? I think it was just something to be emphasized here, maybe in some discussion. So I don't know why that was put here. There's a question, is the energy of 2p pi greater than 2p sigma? The answer is it depends, and so this chart is meant to show you that. There's a question, do the locations of the bonding and antibonding orbitals actually overlap? That's a very insightful question, and think back to what we talked about when we talked about atomic orbitals. Remember we talked about penetration? The 2s orbital could have some electron density closer than some of the 1s electrons. So this is true here also. Uh, these orbitals wind up orthogonal to each other because they're from the same quantum mechanical solution, so they don't have any interaction from each other. Uh, but the electrons think they have their own domain to be in, but sometimes they can be in the same regions of space. Okay, so I think that answered the chat questions. Again, I may need to go back where I got this chart and see what the arrow is. Probably the discussion was that, well, look, we could take this electron and we can excite it up here to the 2p pi star, and that's an allowed transition. If that takes place, we would have one less bonding electron, we would have one more antibonding orbital, and that would reduce the bond order of the excited state of the O2 molecule from 2 to 1. So getting the bond order is straightforward. Again, just count up the total bonding minus antibonding, divide by 2. Okay, well, this is a good place to stop. We'll start next time. In between, you may want to look at this diagram that this shows how well that chart on the previous page actually works. So these are dissociation energies. Here are bond orders that come for various species. And we'll continue with this next week, actually, since this Friday, then we'll have a review for the first exam. Okay, stay healthy, and I'll hang on for a little bit if you have more questions.
I have a question about the practice problems after the quantum mechanics section. I was working on them and I was going through, and I think like some of them, like some of the wave functions here aren't like shown like as answers, and I was wondering, is that like on purpose? Like, are some of them like purposely not shown just to like save on room because it's like repetitive, or
Okay, uh, I noticed there's one mistake on a problem. I give you what I think I labeled it the radial function for the hydrogen 2s orbital, but I actually gave it for the 2p orbital. But then I think the answer solves it for the 2p. Some people have asked me where those functions come from. If we have an exam, I would give you the functions, but there's also a table in your lecture notes that tells you where all the radial functions come from the hydrogen atom. I don't know if that answers your question or not. Uh, I like to also tell people I make mistakes, so I think there may be mistakes in some numerical values on some of the problems. I'll try to correct most of them, but basically make sure you understand how to do those problems.
okay, thank you.
Okay. Okay, take care, everybody.